Okay, so I think we are online, and now we can start with the lecture. So welcome to lecture number 23 of this course on solid mechanics. And today we'll be talking about basically. So basically we will be continuing from where we left in our last lecture, and that is uh, stress equilibrium in cylindrical coordinate system. So if you remember in the last lecture, uh, we did some exercise on this in this line, but that was not complete. So we will continue from where we left in our last lecture. So let me share the screen, and then we can start with the lecture. So okay, I think my screen is visible to everyone. So this is what we derived in our last lecture. So first thing we derived was that total force acting on the Z plane. So this is total force acting on the Z plane and not in the Z direction. So total force acting on the Z plane is given by this formula, which is very similar or exactly similar to what you see in the Cartesian coordinate system. Similar to what we see, we see or we saw for the Cartesian coordinate. This is very similar to that one. The next thing we derived in our last lecture, and we will do it again. I mean, we will not do it again, but we will continue from that point basically. So that was basically Fr. And what is Fr? Fr is the total. So total force acting on the R plane and not R direction. So this distinction between plane and direction is something you should be very careful about, because without this distinction you may get confused. So this is the total resultant force that is acting on the R plane. Now again, one thing you should be very clear about, and that is actually shown here, that when I'm calling total resultant force acting on the Z plane or on the R plane, I am actually talking about both the positive plane and the negative plane. So we are doing a summation of both. So there is one more plane in the cylindrical coordinate, and that is the theta plane. And so today what we will do is we will try to find out the relation or the total force acting on the theta plane. So let us see. So let us go here. And then what I will do is I will start with the same cylindrical element. So the cylindrical element was something like this. So you connect this, and then from here the straight line goes down. You connect this. From here also the straight line goes down. And this is the cylindrical element. Now, in last lecture, I assumed the origin to be at the bottom surface, and we can still do that. But just to be more precise, let us assume this origin to be inside. So it is at the centroid of this mass or of this volume that you see here. And then what is the theta plane? This is my theta plane, right? So in that case, so this is my sigma theta theta, sigma theta theta acting on the negative theta plane. So I will call it sigma theta theta minus, and sigma theta theta minus will be function of, so let us see first. So what is the coordinate of the center? The coordinate of the center is, let us say, r, theta, and then there is z. And now we are taking the centroid of this one, and if it is the centroid of this surface or center of the theta plane, then the coordinate here will be r, and then it will become theta minus delta theta, theta minus delta theta by 2, comma z. So basically, if you draw from here, so this is your delta theta, this angle is your delta theta, and then what we are doing is we are assuming this, since this is the centroid, this will bisect it, and so this becomes theta minus delta theta by 2. So the sigma theta theta minus is function of r, theta minus delta theta by 2 and z. And similarly, I mean, I'm not going to write this again and again, just to save space. So this is my tau, and the direction is z, theta minus, and then this is my tau r theta minus. And all these minus signs indicate that if I'm putting a minus sign here, that indicates that it is a function of these three quantities. What will happen on the positive side? So it is difficult to show here, so I'm just writing it down. On the positive side, we will have sigma theta theta plus, and on the positive side, the point will be r, theta plus delta theta by 2, comma z. So from here, this is delta theta by 2, and this is also delta theta by 2. And similarly, we will have tau r theta plus and tau z theta plus. So these are the different stress components or traction components, because components of traction is known as stress. So these are the different traction components or stresses acting on the two theta planes. So now with this background, let us write down what will be my total traction, or not total, actually you can write only traction on positive theta plane. So what will be the traction on positive theta plane? So I will call it T of minus theta, and that will be equal to sigma theta theta plus E theta, and this will also be E theta hat plus. Why? Because if you remember in the last lecture we talked about this, that ER and E theta depends on theta. So this E theta is going to change because theta is changing. And so at the center it is theta, but on the positive plane it is theta plus theta by 2. So instead of E theta, it will become E theta plus. Let us see. Then there is tau r theta plus, and then it will be E hat r plus, because ER also depends on theta. And then the last term will be tau z theta plus Ez hat. Now here the plus sign is not there because Ez, the unit basis vector in the z direction, is independent of theta, R or Z. So that is not going to change. So that is EZ cap remains as it is. However, for E theta cap and ER cap, because theta is changing, the unit vector is also changing. And that is why we have included the plus sign. Okay. Now let me clear some space. This coordinates, I think, is now clear to most of you. So I'm going to erase those coordinates and all those things. So these things I'm going to erase, and that will basically give me more space to work with. Right. So let us see. Let us see. So, okay, we are almost cleared up the space. And now what we will do is, I mean, we have to use Taylor series at some point, but let us first write down T of minus theta. So in similar line, traction on the negative theta plane is sigma theta theta minus E of, okay, one thing is missing here, and that is the area of the theta plane. And area of positive theta plane and area of negative theta plane will be equal. In both cases it will be delta R times delta Z. So I can write it outside also. So anyways, so this is sigma theta theta minus E theta minus hat plus tau R theta minus E R minus hat plus tau Z theta minus Ez hat. Again, the minus sign is not there because same reason, and the reason is actually that this is independent. I mean, the area is not changing with theta or for the negative and the positive plane. So if you remember, in the radial case, the area was changing, but in this case, the area is not changing. The area is fixed. However, these things, the unit basis vectors are the unit vectors or the basis vectors. I mean, two of them are changing. The third is not changing. Anyways, so what we will do is we will let us work with T of plus theta plus, but there is one mistake here I can see. So there will be a minus sign, and this minus sign is actually missing. So let me see. So on the negative plane, T of minus theta, there will be one minus sign also, right? Now, we are going to use Taylor series. So first we will use Taylor series on this T of plus theta. So let us use Taylor series. So using Taylor's series, and we are going to use Taylor series with respect to this origin, which was R theta Z. So that will be used with respect to this origin, right? So if you use that, this is your first term, and your first term is sigma theta theta plus times E theta plus hat. I can write it to be very more explicit. So sigma theta theta plus is nothing but sigma theta theta at R theta plus delta theta by 2, and E theta plus is nothing but E theta hat at, I mean, R and Z. I mean, so okay, although it is not a function of R and Z, just to be explicit, I'm writing it. And if you write, I mean, since sigma theta theta in this case, I mean, the R is not changing, I can write it that sigma theta 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 plus delta theta by 2, that is at, and then E theta hat at theta plus delta theta by 2. And this is the product function. This whole thing can be written as, say, a function g of theta plus delta theta by 2. And now what we can do, we can use the Taylor series expansion. So g theta plus delta theta by 2, this is nothing but g of theta sorry, by del g del theta times delta theta by 2. And if this is the case, now you go and substitute this g theta, so that the first term will become sigma theta theta times e hat theta plus del theta, and then there is g, which is basically sigma theta theta e theta hat, and then it is delta theta by 2. And this is just one of the term from sigma theta theta plus. So this is just sigma theta theta plus. Without doing any calculation, I can write down tau r theta plus and tau z theta plus. So let us write it down. So I'm going to erase some portion. So I'm going to erase this portion. The top two equation I need, so I'm keeping them. The bottom equation again I will need, so I am keeping them. The middle portion is what is useless at this point, or is not needed, not useless. Useless is not the correct word, but yeah. So anyway, so that is why I am removing it. And I'm going to change the color as well, because to differentiate basically. So this part will be needed. This part I will delete later. So anyways, what do I have? I have this part. So this is your this term. So this term you have computed. Similarly, what do we have? We can write tau r theta plus e r plus hat. And similarly, what we can write? We can write this is equal to tau r theta e r hat plus del theta, then it will be tau r theta e r hat, and then delta theta by 2. What I'm not saying you is that what I'm actually doing in all these things is that I am actually ignoring the higher order terms. So that is something, it is, although I'm not mentioning it again and again, it should be very clear to you that whatever derivation we are doing it by assuming only the first order Taylor series expansion. Okay. So anyways, this is tau r theta plus. And then there is tau z theta plus, and in this case, this Ez is not a function of theta. So that is only Ez. So the Taylor series expansion will only be carried out over this part, and that will give you tau z theta plus del theta tau z theta, and this whole thing will be multiplied by E z hat. So these are the two additional terms. This third term I'm writing again here, and the third term is sigma theta theta plus E theta plus, and that is equal to sigma theta theta E theta hat. So okay, this plus is here and this is here, right? Plus del theta sigma theta theta E theta. Okay, there is one term missing, I can see, hat delta theta by 2, and that delta theta by 2 is missing here. So what I'm going to do is I'm going to erase it and again rewrite it. Okay. So here will be your delta theta by 2, and then the Ez hat will come into picture. So these are the three terms on the positive theta plane. What about the negative theta plane? So now we can delete the red portion below. So let us delete this portion. So then we will do the calculation. So let me delete this one first. Okay. And then now we will do the we will write down for the negative theta plane. So for the negative theta plane, without again doing no calculation, sigma theta minus e theta minus hat, this will be sigma theta e theta hat minus, because delta theta 2 is now minus delta theta by 2, minus minus del theta, and then there is sigma theta e theta hat, and then there is this delta theta by 2, right? So this is sigma theta minus, and then there is e theta hat, and you can write it like this. So basically only this sign is changing. Similarly, I will write down the other terms also. Tau r theta minus e hat r minus, and that gives you tau r theta e r hat minus del theta tau r theta e r, and then there is one delta theta by 2, right? Lastly, the last term is tau z theta minus Ez minus hat, and this is equal to tau z theta. Okay, this I'm putting inside. Okay, so that makes it Ez cap minus del tau z theta del theta delta theta by 2, then again Ez hat, right? And this is your the other three components. So these are the negative z plane, these are the positive z plane. And now what I'm going to do is going to find out the resultant. So basically I'm going to add it up. So basically that is total. So total traction on the z plane, and total traction is basically, remember that total traction is t theta plus t of minus theta. So that is your total traction. So if theta, if I find out, or if I try to find out, so you see when you add tau r theta and this one, and there is this minus sign outside, so this will cancel out, this will cancel this out, and this will add up, and you will get a, I mean, this by 2 will vanish. So the first term is basically what you are getting, del theta tau r theta e r hat. This del theta that you will get after adding it up, I'm not writing it right now. Then plus class, I mean, the rest is quite clear to you. So again, this will happen the same. This will have the same thing. So the next term is also del theta. Tau z theta Ez, and the last term del theta, then there is sigma theta theta E theta hat, right? Sigma theta theta E theta hat, exactly. And then with all this thing, you have your del theta or delta theta, then you have your A theta. So let me change the color. Let me change the color, and then let me change the color, and then apart from this box, I'm going to delete everything else, and then we will work with only this box. So let us erase everything else apart from this box, and I mean, even this diagram on the left I can erase. So let me erase that one as well. So basically, I will only retain the box that you see at the bottom right corner, and then I mean, that's all basically. So look into it very carefully. I mean, there are two derivatives for which, I mean, we don't have the answer as of now, and those are the derivatives that we want to find out. And those are the like, so one of the derivative is tau r theta er. So what will be the derivative? So we know that er and e theta changes with theta, but how does it changes? That also we don't know. So we will try to find that out as well. This portion also we don't need. And let us see. I think this much should be enough for now. I will make more space if I need later. So, okay. So let us continue. And I'm going to change the color once again to say green. Okay. So now, you see if you have this derivative, right? So when you take this derivative, you are going to use the product rule, and you will get a term where you have to find out derivative of ER with respect to theta. So if you want to find out derivative of ER with respect to theta and derivative of E theta with respect to theta, you need so we need to express ER and E theta as functions. We need to express ER and E theta hat as functions of theta, right? Then only we can take this derivative. So let us see. So you remember this z plane. So since there is nothing related to z here, so z, this is this z equal to 0 plane I'm taking. I mean, you can take any z plane. Okay. This is the center, and let us say this is my axis, Cartesian coordinate system. So this is E1, this is E2, and suppose I have a point here, and so this, if I have a point here, this will become my ER axis, right? For that particular point, this is my ER axis. And then if you take a perpendicular from this, uh, that will be your EZ axis. Sorry, E theta axis, right? So that is it. And this angle is your theta. Now from this, so what is ER actually? Let us see. What is ER? You see, from this I can write ER as, so basically I can use the transformation law, and that will give me ER to be, you see, cos. So this is the angle between R and theta. So cos theta, right? And the angle between this and the y axis. So, okay, let me change the color, and this angle, which is so cos theta plus uh, so cos theta plus cos of 360. So if you take 360 will come here, and then you have to subtract this angle, which is 90 minus theta. So minus 90 minus theta. So cos theta will give you the I component if I'm taking it into the Cartesian coordinate system, and this is your J component, right? And if you do the, okay, let me do it first. So this being makes it cos theta I cap plus plus, so cos of 270 plus theta, so that means fourth quadrant, and since it is 270 is 3 times 90, so 3 is a odd number, so that is, this will become sine theta j cap. So this is your ER. So your ER is cos theta I cap plus sine theta j cap. Let us see what is our E theta. E theta is this one, right? So let me change the color once again. So this is E theta. And with E theta, the first thing will be the angle between these two, which is 90 plus. So if this angle is theta, this angle is also theta, and this angle is 90 plus theta. So cos of 90 plus theta I cap, then plus there is cos, so the angle between this is theta, so plus cos theta j cap. Now this is going into first quadrant. In the first quadrant, cos is 0, sorry, negative. So this becomes minus sine theta I cap plus cos theta j cap, right? So what I have done here is I have represented ER and E theta, my cylindrical coordinate system, in terms of the Cartesian coordinate system, and only in R and theta Z is same, so that is not needed. Now let us see what is d ER hat by d theta. So you go here and take the derivative. Sine, the derivative of cos theta is minus sine theta. So it becomes minus sine theta I cap, and derivative of cos theta, derivative of sine theta is cos theta. So this becomes cos theta j cap, which is nothing but E theta, right? You see here. So derivative of ER with respect to theta will give you E theta. That is the interesting result. And then derivative of E theta with respect to theta, let us do that. So sine theta will become cos theta. So this is minus cos theta I cap and derivative of cos theta will become minus sine theta. So this is minus sine theta j cap, which is nothing but minus ER. So these are very important result for cylindrical coordinate system. You should always remember this result. So I'm going to write the result and then delete everything else. So what I can do is let me delete it and then I will write these results. So let me delete this portion. In that case, let us delete this one. And then I can delete this one as well. Because this has been, the utilities has served. So that was the only utility of this representation. Right. So, okay. And then let me write it down somewhere. So I will write it down very small here. And this you should remember, this is a very important result, is equal to E theta, and derivative of E theta with respect to theta is equal to minus ER. So this portion I'm not going to delete. So this portion we are going to use. So now let us go back to this one. So what do we have? Let us say F theta is equal to, let me change the color so that it don't matches. So I want to use magenta. So there is, so let me open this bracket. So that will give us del tau r theta del theta er cap plus tau r theta del, er is only function of theta, so I can write it d. So d er cap d theta, and quite clearly I'm going to write it as e theta. So let me write it down, delete it, and write it as e theta. So that is the first term. Let us come to the second term. There is nothing. So let me just write it down. Del tau z theta del theta. There is Ez. And now let us come to the last term. And there we have a product rule there. So first it will become del sigma theta theta del theta e theta cap, and then it will become minus, because del theta of e theta is minus here, so I'm taking the minus on the left hand side. So minus sigma theta theta er, and you multiply it with del theta, and then there is a theta is nothing but del r del z. So we are going to take 1 by r outside. So this will give me 1 by r. And now we are going to couple this together. So like there are two er. So we are going to write it together. So that is del tau r theta del theta minus sigma theta theta. And then you multiply it with er hat. Right? Then there is e theta. There are again two terms. So that is tau r theta plus del sigma theta theta del theta, and you write e theta hat And then lastly, there is so basically this and this have been coupled. This and only Ez is remaining, and Ez is the easiest one. Del tau z theta del theta Ez hat. Now I have put 1 by r here. So on this side I will get what? R delta theta, and then delta r. I mean, okay, I was using small r. So to be consistent, let me erase this and this. So since I'm using small r, so I should write smaller, and then delta r, delta z, and this is nothing but delta v. So this is the final expression. So let me delete it, delete everything else basically. So if we have our f theta now finally, to combine or to associate it with fr and fz, which were computed in the last lecture. So we are now ready to do the momentum balance. I mean, the class was the title of the class is linear momentum balance, but we have done everything apart from that. So what is f theta? F theta is 1 by r outside, and then inside the bracket it is del tau r theta del theta minus sigma theta theta, and then you have the er plus del sigma theta theta del theta plus tau r theta e theta plus del tau z theta del theta ez, and then you have your volume. So this is your final f theta. So let me see it once more so that I can write it without seeing it. So okay. So what we do now is we go here, and so we have our fz and fr. Let me write down f theta now. F theta is 1 by r will go outside, and then what do you have? You have del tau r theta del theta minus sigma theta theta, and this is er cap plus del sigma theta theta del theta plus tau r theta, and this is multiplied by e theta cap plus del tau z theta del theta, and this is multiplied by ez cap, and then your total volume. So this is your fr, f theta, and fz. So we have all the three components now. So now, and these are total forces acting on a plane, say on r plane, z plane, and theta plane, and not in a given direction. Now, if we want to do the linear momentum balance, say in r direction, so let us say I want to do linear momentum balance in r direction. Okay, right? So what we can do, we know force is equal to mass into acceleration. So that is what we are going to do. So what are the forces that are acting in the r direction now? So anything that is er hat in the expression is acting in the r direction. So those are the forces. So let us start from this one. So we have from the FR, we have delta sigma RR delta R plus sigma RR by R. This is coming from FR. Then you add it up with F theta. And in case of F theta, what is acting in the R direction? You have 1 by R common, and then you have del tau R theta, del theta minus sigma theta theta, right? And then from the Fz, you have this one, no, not this one, this one. So del tau Rz del Z, and then there is okay, E is, we are not writing E because it's momentum balance. So this is the total force that I'm getting from the three things. Now someone was asking about body force. So along with these forces, there can be body force, which is BR in this case. Now you see it was all was multiplied by del V, which I have not written. So let us multiply it by delta V, and let us say, so that is equal to mass into acceleration. Mass is basically, which is equal to rho delta V times acceleration in the R direction. So this delta V will cancel out, and your final expression, which I'm writing it here, you see, delta sigma RR by delta R plus 1 by R delta tau R theta by delta theta plus delta tau RZ by delta Z plus sigma RR minus sigma theta theta by R. So this is the equation plus BR, and you can write it to be equal to 0 if you assume your acceleration to be, so if you assume there is no acceleration. So this is your stress equilibrium equation in the R direction. So if you look carefully, and let me change the color actually, so you see this term and this term are similar to the linear basis, so to the Cartesian cases. What has happened is whenever there is a theta, 1 by R is coming into picture, and then there is one additional term which is coming up, and this additional term, why is it coming up? Because on one end the area is not same on the positive and negative R plane, and on the other hand your basis function, unit basis function or unit vector is changing with theta. So that is giving us this additional expression. So this is what we get in the R direction. So let us do in the theta direction. Z direction is the most boring one because that will give you the same result. So let us do it in the theta direction. And you will see again the same thing. One additional term will come up, and whenever there is something related to theta, I mean derivative with respect to theta, one R will come up, 1 by R. So we are now doing it in the theta direction, right? So from this expression, I will take the theta term. So that is del tau theta R del R plus, so this term I'm not writing now. Remember, this term I have not written yet, but I will have to write at some point. Then let us go to the F theta one, and in this case we have this term. Again, I'm only writing this term. So we have del sigma theta theta del theta. So again, this term I have not written, which I have to write. And remember, this is wrong because this 1 by R is there. So 1 by r will come outside. And again, you see, whenever we are taking derivative with respect to theta, 1 by r is coming. Plus, so this is, we are doing in the theta direction. So this one will come up. Del tau z, del z. And now I'm going to write down the terms that I neglected earlier. So what do I have? I have tau theta r and tau r theta. Now we know that sigma xy is equal to sigma yx. Similarly, tau r theta is equal to tau theta r. So that makes it twice tau r theta by r. Then there is the body force. You multiply it by volume. So that will ultimately cancel out, but still let me do it. And then there is mass, which is rho times volume, acceleration in the theta direction. This cancels out, and then if there is no acceleration, or the velocity is uniform, in that case we can remove this part, and this becomes equal to 0. And you can check again whenever there is, with respect to theta, 1 by r is coming into picture. Let us go to the z direction. So in the z direction, so what do we have in the z direction? Let us see. So first we have delta tau z r del r. This one we have taken. This is yet to be taken. Let us go to theta, and then in the z direction it is 1 by r del tau z theta del theta. And then let us come here, which is this one, not this one, this one, plus del sigma zz del z ez will not be there, sorry. So del sigma del zz del z plus the term that we had left out is tau zr by r, and plus you add the body force in the z direction, and that will be equal to 0. I mean, assuming constant velocity or no acceleration. So these are the three equations actually. So these are the three your stress equilibrium equation for cylindrical coordinate system. So what you see here is that some of the terms repeat itself, I mean, or are similar to Cartesian coordinate system. And then there are terms which are new, and these new terms are coming up because if you look into the r direction, what you see is in the r direction the area changes, and in the theta direction the basis vector changes, and that is resulting in newer terms coming up, and also a 1 by r is coming up. So that is it for cylindrical coordinate system. I mean, not cylindrical coordinate system. That is it for linear momentum balance. So this is so these are the three equations that we just derived. This one, and this one, right? And what I will do is I will stop here now. So that is it for today's lecture. And in the next lecture, we'll talk about strain in cylindrical coordinate system. Okay. So thank you, and we will see again in the next lecture. Which will be after some time because of this break and the mid-semester break.